In this video, we're going to talk about the fundamental theorem of line integrals. The fundamental theorem of line integrals says that if we are computing a line integral of something that looks like gradient of a function dotted with vector dr, then the way that we evaluate that is just to find this function little f and to evaluate it at the endpoints of our curve C. We can think of this as being a generalization of the fundamental theorem of calculus that says if you integrate a derivative, let's say we integrate f prime of x with respect to x over a certain interval from a to b, then the way we actually perform that integration is to find the function f of x, meaning find the antiderivative, and then evaluate it at b and then at a. So let's do an example of the fundamental theorem of line integrals, and one of the things we're going to focus on is this notation, just to make sure we're comfortable with this idea of what the gradient of f dotted with vector dr is going to look like. So first, let's talk notation. We could recall from one of our previous videos what this vector dr represents. So vector r, just think of that as your position vector. That looks like x, y, z. And if you pass the differential operator onto those components, then you get dx, dy, dz. So vector dr, just a quick way of saying this vector dx, dy, dz. What that does for us is that allows us to write an integral in a more concise way. So if we look at the integral that we've got in the question, we could say it's the line integral along C. Well, let's express all this stuff here as a dot product. So it's going to be some vector dotted with dx, dy, dz. If we write down the components of the first vector, it would be y, x minus z sine y, and then cos y. So our integrand has the form some vector dotted with vector dr. So let's call this first vector here capital F. So think of that as a vector field. And the idea is that if this vector field is conservative, then we can use the fundamental theorem of line integrals to solve the problem. So as the next step in the problem, I would ask, is our vector field equal to the gradient of some function? And because our vector field has three components, the way we check that is we calculate the curl of our vector field. So let's do that. So curl, going to be a 3 by 3 determinant. We're going to have our ijk, then we're going to have our partial derivative operators. And then we've got the components of our vector field. So y, x minus z sine y, and cos y. So let's expand along the top row here. For the I term, we're going to take that product there. So partial derivative with respect to y of cos y is going to be minus sine y. And then if we go this way, we're getting a plus sine y. So first component is definitely 0. For the j component, we're going to have 0 minus 0. So we get another 0 component. And then for the k component, 1 minus 1. So just going through those details very quickly, yes, curl of f does come out to the 0 vector. So the answer is yes, our vector field is conservative. Now that we've decided that it's conservative, we need to find a potential for our vector field. So we talked about that in our previous video. Basically, the idea is to go through and integrate our components with respect to the appropriate variable. So f is going to be the integral of y with respect to x. It's also true that f will be the integral of x minus z sine y with respect to y. And it's also true that f will be the integral of cos y with respect to z. So putting all of that together and going through the details quickly, what we find is our function little f looks like xy plus z cos y. Okay, and then let's flash back to the fundamental theorem for line integrals to just see how we're going to put all this together. So the idea is that if you've got a line integral and your integrand looks like gradient of f dotted with dr, then you're just going to evaluate that function f, which is our potential function, evaluate that potential at the endpoints of C. Okay, so let's put it all together now. we decided that our integral could be phrased like this. So let's rewrite that. So the integral in the problem is a line integral along C of some vector field dotted with vector dr. And we just went through this work of figuring out that yes, f is conservative. So instead of writing vector field f there, we can write gradient of little f, because we know that our vector field does have this potential function. And because of that, when we integrate the gradient, what we get is just our potential function, and that's going to be evaluated at, let's say, b and a, which are just the endpoints of our curve. All right, well, our potential function was xy plus z cos y. And we can look back at the statement of the problem just to grab our endpoints. So we were told the endpoints of C, 301 and 4 pi 5. So we'll evaluate first at 4 pi 5 and then at 301, and we'll have the value of our line integral. So plugging in, we're going to have 4 pi plus 5 cos pi, which is going to be -5. And then we'll subtract off the value at 301. So that's going to look like 0 plus second term is going to be 1 times cos of 0. So that's just 1. So in other words, final answer, the value for our integral, 4 pi minus 6. So I want to look back over this question quickly and realize how efficient that fundamental theorem of line integrals is at computing the problem. So basically all we had to do to solve this problem was to find a potential function. So once we found that little f, then we just had to evaluate that function little f at the endpoints of our path. We did not need to parameterize the path. In fact, we didn't even know the path that we were traveling from 301 to 4 pi 5. So we couldn't have even done a parameterization if we wanted to. So we had to find that potential and then evaluate it at the endpoints. So just as a quick recap here, let's say someone gives us a line integral of something that's in the form vector field dotted with dr. There are two cases here. I would say the nice case is if our vector field is actually conservative. So if there is some function little f out there, so that our vector field is the gradient of that function, then you can use the fundamental theorem of line integrals to solve the problem quite quickly. If your vector field is not conservative, so if there is no function little f out there, then you would need to parameterize the curve. In that case, you'd need to have information about what the path is, what path we're taking between the endpoints, and then you would solve the problem as we did in our previous videos. Thanks for watching.